Thanks for braving the weather. Today it's going to be a new module I'm trying out for this semester. It involves the mechanics and materials of Leonardo da Vinci. So before we get into the lecture, just wanted to touch base. Does everyone have access to the Stellar website? All right. There's been, under the homework tab, there's been the insertions for your half-page paper topics, and the due dates have been listed on the Stellar website. So the first deliverable is going to be the half-page topic. It's due February 21st, okay? And once that gets reviewed, you'll either get an email from me saying you're good to go work on your paper, or if you need to revise the topic, make it more narrow in scope.
Full screen? No, full screen.
Yeah, I was going to leave it like this.
I can't read fine print.
All right, so the tentative layout for this module. For the most part, the lectures are going to deal with Da Vinci as war engineer designer. Most people know him for his artwork, Da Vinci, The Last Supper, but this is going to touch base more on what he designed in terms of weaponry, okay? He's known for catapults, flying machines, as well as underwater apparatuses, so scuba designs, things like that. What the intent of the module is going to do is going to show you what the state of the art, what his ideas were in the 1450s to 1500s, and then try to tie it into modern day technology, whether it's for submarines, whether it's for shipping, army, tanks, those types of technologies. The secondary interest for the module relates to Da Vinci's designs as a bioengineer. He did a lot of designs on the human body with respect to the heart, the rib cage, different parts of the body, the cardiovascular system. So now, in the 21st century, you can look at that also as a method for warfare, all right? Biological engineering is now going to be the new threat realm for war, all right? It's not just going to be tanks and weapons. So we're going to touch on, first and foremost, the catapults and the actual machinery structurals, and then look at it from a more human side with respect to bioengineering as well. This module came as a result of a visit I made to Rome, to the Da Vinci Museum over there. So part of the module is going to show some interactive designs and mock-ups that they had at that museum. So a little background history on the man. Da Vinci lived 1452 to 1519. He was the bastard son of a wealthy Florentine notary and a peasant woman. So there was issues in his life growing up, the fact that his father didn't want to recognize him. Whether that was a chip on his shoulder or not, he decided that he would go and end up being an apprentice for the artist Verrocchio at the age of 14. And at this time, this is around the Renaissance era in Italy. Florence was the location where a lot of the great masters of the day, Michelangelo, Raphael, that part of Italy was where a lot of both artistic work as well as engineering work was being performed at the time. One of the things we'll talk about is at that time there was a lot of interwarring between factions within Italy. So in 1482, he moved to Milan and he entered the service of the Duke of Milan. And it was around that time that he would get consignments for not only his art and his sculpture work, but for what we're going to talk about in terms of the weaponry, catapults, and other machinery. That was for both the Duke of Milan as well as for the Medici family, which was the big banking family at the time in Italy. 1499, France invaded Milan and other areas of Italy. Da Vinci moved to Florence as an engineer for Cesare Borgia, and that was where additional engineering work was done on his part. And his last years of his life, after the French conquest of Milan, he actually spent working for the King of France. So that was King Francis. One interesting thing I will add. So this image here, if any of you are aficionados of art, one of Da Vinci's famous paintings is a self-portrait of himself as an old man, which is referenced by many people incorrectly. It was how he envisioned himself later in life. It's not an actual portrait of himself. So that's something to note if you ever see the painting Da Vinci as himself as an old man. It's how he thought he would view himself in older age. So his contributions are not just limited to the arts and sculptures. What we're going to talk about today, I'll show you some schematics and mock-ups. He looked at nature and he tried to take nature and make it into a scientific form. So air and wind, he was known for his flying machines, catapults, cannons, steam machines, but also due to his skill and artistry, the anatomical design of the human body. So I'll show you some sketches that he did. The detail on the sketches is very impressive. So you'll look at it. He also came up with his own unit of measurement. If you've seen the Vitruvian Man, which is another one of his famous artworks, he came up with his unit of measurement was called the cubit. And he ended up making generalizations for science warfare designs based on just geometry, correlations between the length of arm versus the length of legs and hands and things like that. The physiology, kinesiology, all right, the organ functions as well as mechanical interaction. So he actually took corpses and basically did his own biological teardowns of the human body. He looked at the design of these war designs. Just basically, he did that so he could spend more time on his artistic and musical interests. So there's lesser known things about Da Vinci were his interest in music. So some of his ideas were influenced by the designs of musical instruments and things like that. The thing that I found very interesting is he had no formal training in engineering. So it's basically self-taught, and it was based on what he saw in nature and the things that interest him. A lot of it was interaction between the wind and the water. And you'll see a lot of the designs are based on things that are that simple. I was talking with Steve, and we have another module this semester. It's on intellectual property. And one interesting note about Da Vinci that I thought was very interesting was back in the day, there was a lot of concern that people would go into his workshop and steal his designs. So he actually, back in the 1450s, had a method of himself of inserting intellectual property into these designs. So what he did was, in his writings, all right, if you were reading the writings from right to left, he would use a special calligraphy or a special font, and he would use palindromes. So if somebody was walking into his workshop, they would just read his work, and they would read it from left to right. But he had made small notations to himself, so those palindromes should be read the opposite direction. So if somebody tried to mimic his work, they would not have gotten the correct output from the design. So it's a very, simple way, but he actually considered the intellectual property even back then. And there was a lot of stealing of ideas in these workshops back in the day between these people. So in terms of engineering mechanics, in the lectures we're going to talk about, there's going to be issues related to the strength of materials. Fluid mechanics, as I said, is going to be a big thrust of his knowledge. So turbulent versus laminar flow. So what you're seeing in this drawing here, his hand drawings, the detail here, he made this with a hollowed out wooden tree trunks, and he did his own water type tests. And what he did was he was able to determine the eddy flows and the air pressure over the surfaces as there was connections in these wooden branches. So he also worked with aerodynamics, air pressure over surfaces, Bernoulli's theorem, things like that, as well as pulleys and levers. So what you're going to see on some of these schematics is the interaction of how he had multiple gears moving at the same time to ultimately get lift versus drag for a lot of these flying machines or other types of catapults. In terms of architecture, at the time, there was Michelangelo doing Sistine Chapel. He was particularly interested in geometry of the arches and structurals of that sort. So he did a lot of engineering work with respect to architecture for the Duke of Milan. Also, he did bridge design. So in one of the later lectures, we're going to look at what his truss and bridge structures were versus in the 1800s and Industrial Revolution, how some of the bridge designs in US and other countries came about. This is before Bessemer process, before the Industrial Revolution. So there's not really much ability to build these structures out of steel at the time. What you're going to see in the mock-ups is it's mostly fitted connections with wood. There was iron, brass, and bronze, but most of these structures that you'll see are essentially engineered lumber products. And the fittings and the gears is what made it work. So a background on the wars that were going on. They were referred to as the Great Wars of Italy, and they went on for about 60 years. They were also known as the Habsburg-Valois Wars. This was a time where there was a lot of fighting between France and Italy. So this had to do with the royal families in the various countries. So what happened was he was commissioned by the Duke of Milan. Basically, the Medici family said they would pay him. They wanted his designs. And one of his initial designs were for catapults and military tanks and capable of moving soldiers and submarines. His understanding of siege tactics was used especially with respect to his designs for tanks. So these tanks, you'll see in later slides, basically were able to have soldiers inside the tanks, and they were able to use gears on the inside of the tank to move and protect them from receiving ballistics. This is about 450 years before World War I, where we would consider that would be the first time that modern tanks were used in the warfare. So his hand sketches are what we're going to look at for the most part of today's lecture. All right, what we're seeing here, this was the exterior of his tank design. He also designed cannons and catapults, steam cannons, and other types of devices. And the flying machines were a second set that he designed. Now, the flying machines, even though he was able to design these mock-ups, they were not necessarily ever used in these wars. But as part of his design, they were something that was made available. Of more interest would be the catapults and also things related to wind motion. So in modern day, there's plans to build offshore wind farms off the coast of the East Coast here. One of his early designs was essentially for an early anemometer that would measure wind speed that you could use for that technology is still applicable today. So the vertical flying machine. What we're going to see here, this is just a wooden mock-up of the flying machine. It has a retractable ladder. So when you're thinking of the scale of this was like, I believe it was about 12 meters or something in length. All right. So somebody would have had to climb in and the ladder would have been retracted. It required the use of all limbs. It used both limbs, it used both arms, and it actually also used the individual's head to generate the energy for the lift. But you had a retractable ladder here, and you also have multiple gears on the bottom here that are coupled to these wings. And he referred to it as a beating crisscross the way a horse moves. So if we're looking here on the video, you have this lever arm, and it connects via these gears and pinions, and you'd think of it basically as a sun fan or something, but these are how he incorporated his designs on the movement. At the time, they didn't have carbon fiber composites, so it was basically the fabrics that were available. So you weren't able to weld things, you weren't able to join them in the manner that we do today. So the goal of the module is to show what was available back then and then tie it into what we're using today. In terms of his aquatics and hydraulics, he believed water to be the driving force of nature. So a lot of his designs were built on that idea. He actually designed a scuba system in the mid-1400s that you'll see in the later slide that resulted basically in air sacs that somebody could walk underneath a moat, and then they could basically sabotage the enemy's water forces at the time by using this scuba machine. So the interaction of air, including waves and currents, was a big driver. We're going to talk about his double hull design as well, and that will probably be a case study in and of itself with respect to Exxon Valdez failure. So he had a design for double hull technology, and that was very different from what was available at the time. Now, in 21st century, on shipping containers that go cross-shore, they design double hulls into their structure for impact resistance. If you know the Titanic, you know why they designed these double hulls. So if you hit something, either a sandbar or something of that sort, back in the day they had a round bottom on the boat, and it would basically sink the boat, single impact. So the double hull design was very advanced for its time. This is a schematic or mock-up of his scuba design. So what you're seeing here is if the individual was under the water, these air sacs would fill up and allow somebody to walk underwater. Now, I have to look and see at what depth they would do this, but for the time, it seems like it was for moats, so it doesn't seem like it was very deep where the scuba machine would work. But they have essentially a pipe that would lead up here. You'd get the air into these sacs, and somebody could walk underneath the water. He had designs related to multi-directional guns. So in terms of the weaponry, each one of these openings would be able to have a projectile come from it. And he designed the bullets in this manner for aerodynamics, which was also unheard of at the time. If you look, you can see the fins on these bullets, and the hollowed out area of these Ogival bullets. That was for aerodynamic efficiency, and that enabled these bullets to travel further than the opponent could shoot theirs back at their side. The tank design, as I stated before, it has gears and wheels on the inside of the tank. So what would happen is they would actually have soldiers inside this tank, similar like the Trojan horse, where there was people inside the structure. They were able to move the tank via these gears, so they could close the hatch, move. This is actually, they could send out bullets from these various openings as well. So they could walk and move while they were also sending projectiles down. So this is early design of the tank. What I will do in a later lecture is probably show you some designs for Abraham tanks or some American tanks that we've used in the past 50 years or so, and show you the difference between, this is 1400s. I mean, this is not going to stop, metal ballistics, but the purpose of it is to show that he actually thought that let's have people on the inside protect them and be able to move rather than just be a stationary target. He designed interlocking bridge designs. So this bridge design has no rope and no nails. All it is basically a fitted connections where the wood interlocks with each other. And they could manually put this together to go either over moats or over small buttresses, fortresses of the time. There is no, in terms of the joining or fastening, there is no wires, no ropes, no metal, no rivets. It just fits together, so it's easily put together and it's easily broken down. And here's a mock-up of it at the museum here. So you see the interactions here. There's no adhesives holding this together. It just fits together based on the machining or how he made the wood fit together. So the double hull vessel, here's an image of the double hull vessel. So you see your outer hull here. Back in the day, this bottom area would have been a round bottom curvature. So what would have happened if there was any type of impact, you could breach that outside hull and then the vessel would no longer operate. With the double hull, even if you breached the outside vessel, you were able to still float. Unless you breached both of the hulls, the vessel would be able to still operate. We'll discuss Exxon Valdez. And after Exxon Valdez occurred, the government made changes to designs of these shipping containers, so it was mandatory to then have double hull vessel for if it was had oil as the product that it was carrying. So the flying machines, he had two types of flying machines designs. They're predecessors to rotorcraft, and this is the flying machine here where he would have people moving with both arms and legs. And you see it's almost like a helical, double helix type design here. There was a second flying machine where it almost was like Icarus, where the wings actually had some movement to them and an individual would go on these. These were not used in the warfare, but the designs were made nonetheless. And it's interesting, we'll show in some of the mock-ups, compared to current aviation technology, what we were at there. So with respect to this, I wanted to ask, are there any aerospace engineers, people doing aero here? All right, so if you're familiar with surge stall conditions, we're going from what Da Vinci made in 1450s with basically fabrics and gears and pinion connections. This is going to be a video. It's a surge condition on takeoff. And this was actually, from my recollection, I believe this was a demo engine. And they purposely left out a couple blades. So what you're going to see when the video starts is there's going to be some vibration. And it's this engine's going to rock back and forth, and then you're going to see uncontained loss out the back of the engine.
Brian, what does surge mean?
Surge is when the engine actually thrusts back. So
Means surge, it goes in the opposite direction.
yeah.
I get it.
So you see the movement here? There's some vibration. And then you see out the back, out the exhaust. So this is right on takeoff. As you see, it's leaving ground. The vibrations increase as the angle goes up, and then that was your uncontained release out the back of the engine there. So this is relevant to, we're seeing more airplane accidents in the news these days. So not necessarily, this isn't necessarily what's happening with the 737 MAXs, but there have been some uncontained engine failures recently. Years ago, the FAA used to put out a bulletin every 5 years or so on uncontained engine report on all commercial aircraft, and it would list how many aircraft had these types of uncontained failures. And that is when it either loses a blade, or it's even worse if a disc fractures. But what happens, as you see, if it starts in the compressor section, so those had blades removed from compressor section, they then get ingested through the rest of the engine and out, and you see the destruction as it goes through the engine. So as Professor Egers mentioned on a lot of his lectures, if you're ever on a plane, in general, you'd want to be on a 2 or 4 engine plane, because even if that happens on a 2 engine plane, the pilot is usually able to maneuver with the other engine. So I have some additional videos we can show with respect to the Miracle on the Hudson and the double bird strike. FAA, as part of their engine certification, has tests where they have a full test cell and they throw in, it used to be live chickens, but I think now they're frozen. And they...
No, that story is, yes, I told that story, but they would throw in a dead chicken. But the British were developing an engine and they kept on failing. They couldn't pass the bird strike test. And so they wrote back to the United States and said, we can't pass this test. And the guy from the US wrote back and says, fresh, not frozen. They were throwing in frozen chickens. And you never hit a frozen chicken blind.
So in terms of the flying wing design, there's also the speed gauges. So when I looked at this, what I thought of was the old steam engines that Mark Twain talks about on the Mississippi River. This is both for wind and water, but you're seeing that's moving the entire, windmills type structure there. So Da Vinci had these aerodynamic designs that he built 500 years ago. What you're seeing here is a lot of the designs were based on human. They were there was no motors. It was humans were moving these things to make the device work. So what you're going to see when it goes to the bottom, you see multiple gears moving, and that generates the wind device moving on the top. And it's the interaction of these two gears that moves. Now, he made, with these fabrics, it's generally, these things are going to be lightweight. All it is wooden fabrics. So if we go back to the movement on the bottom, this interaction here is powering what's going on up top. So it's just a coupling of the gears.
Did any of these things get off the ground, either in the form of a model or a working prototype?
The museum says, for the most part, no.
The only way they look like they fly is if you throw them off a building or something.
Well, you have to realize that he was also probably hundreds of years ahead of his time, because they still thought that the the sun rotated around the Earth around that time. So one of the interesting things that I see though is the interaction of these gears for the movement. All right. And when we talk about the submarines, I thought this design for submarines was very interesting as well. Have any of you guys heard of a Rube Goldberg machine before? So when I looked at this, I kind of saw this as a very elementary Rube Goldberg machine, but there's no candy or toy popping out at the end of it. But it relies on a lot of gears. When you looked at his design, there was quite a bit of gears and movement involved. So here's his sketch for the vertical flying machine. So he believed that a pilot could actually use this to get off the ground. It's unconfirmed based on what I saw whether it actually was successfully used or not. But in terms of the dimensions, this thing was 40 feet long, all right, an 80-foot wingspan, and the 80-foot wingspan is what was used to generate that lift. But it also required somebody to use both their arms, legs, and head. So you have, imagine trying to move all these things simultaneously. And then there's sliding mechanisms to move up and down, generate your liftoff. As I had said, it also had this retractable ladder, and it had shock absorbers. So he even considered inclusion of shock absorbers into the design back then. One of the things, this will probably be its own lecture. So the bioengineering. These are his hand-drawn sketches of various parts of the human body. And I thought, when I looked at them, I was really blown away by the detail that he included. So there's designs for the skull. He basically was a medical doctor back then as well, looking at the human body. I'm going to include some journal articles on Stellar, in particular related to his work with the cardiovascular system as well as human ribs, his studies on the biomechanics of those things. But you'll see the bioengineering here in the sketches and a follow-up here on the human skull and various parts of bone structure. So this is where he actually looked at features of different corpses, and he made measurements on the body between hand and arm, and that is what he ultimately used to make some general correlations that ended up being this Vitruvian Man design. Or it's artwork, but it's an engineered artwork. So some other photos of cannons and things like that. The one other thing I did want to show, let me see if I have it on this DVD. While this thing's loading, all right, how many of you guys are planning on being practicing engineers, professional engineers? All right. One of the things I wanted to talk about is when you go to take your professional engineering test, this is called the Fundamental Engineering Guidebook. It basically has all different disciplines of engineering on little short 1-2 page discussions. So with respect to the human body, I'll pass this around, you can look at it. The biomechanics of the human body is described here. So just look at some of the forces involved in this simple force diagram, and then look at the flying machine and think about the forces involved in both the arms, the legs, and the head.
Fun fact about Da Vinci, he dissected 30 decomposing corpses that he received from the religious people in his town that photographed.
He got them from there.
It's something called the Vitruvian Man, is what he believed to be a connection between the human form and the universe. That picture of the skull with the muscles here, that's called the Vitruvian Man.
This is another view of this engine surge stall condition. What's going to show up afterwards should be the back view. Anyway, I'll show it to you at a different time, but what you're going to see on the surge stall is that when the blades actually came out of the back of the engine, you see it's essentially an explosion out the back of the engine, and they have cameras set up to show the rear view of that surge stall condition. So with respect to aerospace current technology, all right, we go from looking at his vertical flying machine. For people in doing materials as well as aerospace, one of the key parameters for engines for efficiency is what's known as the turbine inlet temperature. The turbine inlet temperature is primarily a function of the material used to design these blades and the discs. All right, we went in engineering side from single crystal alloys. We had directional alloys to single crystal alloys. As you increase this turbine inlet temperature, and I'll pass these and you can look at these, with the technology today, the engine blades actually operate beyond their melting point. So how they've made that possible is by inserting cooling channels into the blades, all right, with these very complex geometry on the insides. And what you'll see when I hand these out is actually, when we're dealing with turbine blades, it's not just fatigue from the pressurization cycles, it's also creep. All right, so that's extended time at an elevated temperature for these blades. So this is particular to turbine blades, but it also affects your compressor blades, and it also affects other parts of the engine. So when you look at this, you can look at the progression of the aerospace industry with the materials technology. The last couple things I wanted to mention today, if you guys don't have any other questions on these slides, is for the people who are material science undergrads, one thing I do recommend, if you haven't seen, this is ASM Handbook. It's the American Society of Metals, all right? One of the options, and I said this in last semester in a previous module, you can sign up as a student member for ASM. It's like $15 for the year, and I highly recommend it. And if you want to, if you're gonna be in grad school and doing research, you can get a student rate on this. This has 25 volumes related to different material properties. So iron, corrosion, other mechanisms. So when we talk about future lectures, when we talk about steam cannons or we talk about other devices, I'm going to try to tie it into the materials side, whether it's talking about corrosion, whether it's talking about wear, friction, or other degradation mechanisms. But if you are planning on doing research, you can get over 50% off on that, and I think it was worth it for when I did my research. The other option is, as MIT students, you can access Novell, which is an app which you can get journal articles, and you can do keyword searches for your research projects. So, do you guys have any other questions related to the intro? So that's all I had for today. If you have specific interest with respect to Da Vinci's designs, so if somebody here is in the Navy and is interested in the submarines, I can add slides related to specific components. But the intent is to show you his initial designs, Not all of these were actually put into service. Some of them were decades and centuries ahead of their time. But it's going to try to tie in his early designs towards current technology. So that's going to try to be the goal for this module. Thank you.